Yeah.
Yeah.
Okay, well, folks, good morning, everyone, for this distinguished webinar series in AI and cybersecurity. Today's distinguished speaker is Dr. Binh Nguyen, Senior Researcher, NREL. Dr. Bang is a senior member of IEEE, received his bachelor's in engineering and master's in engineering in electrical electronics engineering from the VNU HCMC, University of Technology, Vietnam, in 2010 and 2013, respectively. In 2015, he was with Eastern International University, Binh Duong, Vietnam, as a lecturer from 2016 to 2018. He was a research assistant in the Power Electronics and Magnetic Design Laboratory, Kyungpook National University, Korea. He got the Ph.D. in December 2022 with Smart Power Systems and Controls Lab, Clarkson University, Potsdam, New York. From June 2021 to Feb 2023, he is with National Renewable Energy Laboratory as a graduate student researcher. From March 2023 to August 2024, he is a R&D engineer at AOT-RFE Group, LANSCE, Los Alamos National Laboratory in Pulse Power Systems. From August 2024, he is with NREL as a senior researcher. He received the IEEE Best Paper Award for IEEE Industrial Electronics Magazine 2020 and the IEEE NPSS Early Career Travel Grant. His research interests include signal processing, control machine learning, power electronics, and power systems. Dr. Bang, it's a great honor to have you as part of a webinar series at UND. Thank you so much for taking the time this morning with us to share your insights on microgrids. The floor is yours. You should be able to see the screen. I shared the screen.
Okay. Yeah, thank you very much for your invitation and also nice introduction. So can you see my slide right now?
Yes, we're good.
Okay. So my presentation today, actually my PhD thesis. Yeah, that's the model by dynamics and state estimation and deep learning on graph for fault detection in microgrid and active distribution system. So like you already introduced, I am currently a researcher level 4 at NREL. First, I will talk about the objective and the application of the work that I have done. So in the objective, we know that the situation awareness is the ability to comprehensively identify the system state and correlate abnormal conditions pertaining to control and management process. So there are like three main applications related to situational awareness, is like the state estimation, the parameter identification, that provide the estimates of states or parameter of the system. And from that we can identify the bad data and also the abnormally that discerns the abnormal behavior via measurement data. So we to do that we need a baseline of normal and good, like you redefine. And the first application is the fault or event detection. So we be able to detect the fault or some like big event, important event, with that the signature are known or redefined, so that we can differentiate from like a specific event through a normal operation of the system. So in the left, I have a few of microgrid and active distribution network. So it have like connection to the main grid, and we have the supervisory control and management, and our situation awareness will support the supervisory control and management. So if we have the faults, we have events, we have like normal operation of system, and we can use all of that data to comprehend the situation awareness. And beside that, we may have the cyber attack go through our communication channel and like change our data. So we can see the system different from the true state of the system. So here I want to talk a little bit about two main approaches in situational awareness. That's the model-based approach and the data-driven approach. In like four key factors, that's the model, the derivation, the merits, and challenge of the two approaches. First, about the model, like the model-based approach, based on physical rules and constraints that we have some estimation or classification function like mathematical function. But in the data-driven approach, we have machine learning algorithm, we have the neural network structure. Internal derivation, in model-based, we use some system identification technique. We have some regression techniques. In the data-driven, we have to train the data that we collect from the system, and that is the training and learning process. The merits of model-based approach is that is like inheritance and accumulate knowledge. So based on the model and based on our equation, our understanding physical law of the system, we will know more and more about the system, and based on like everything is just like is learnable and based on the reasoning. So that's why we have like more and more knowledge of the system. In the data driven, we have many data, but we need to distill the knowledge that we get from the data, and we like no require real knowledge of the system, and the model we have in neural network is non-linear and stochastic. So it's good to learn a very complicated system without no physical law of the system. So the challenge of the two approach is that for model-based approach, it quite like on the physical law and equation and function is quite complicated. And they have like non-linearity, the stochasticity, the unobservability. The challenge in the data-driven approach, we have to have like sufficient data, and when we train the data, we get the results. We may face the problem of unexplainability. We have a problem of overfitting, underfitting, and bias in the data that we collected. So there are like no best approach, like no one approach for all problem. Only we have to find suitable approaches for a specific problem. So in my work, I focus on like two applications. So in the figure in the left, when we have many measurement data, we have historical data of the system. We have the redefined system parameter, like the capable specification, the distance, and also the environment condition. So we can choose like three architecture of our framework, like the distributed one, the hierarchy one, or the centralized one. So in the approach, we may choose the model-based approach or data-driven approach. So there's some approach that misses like the model-based and the data-driven base. So we can have the misses or the hybrid approaches. So for the tasks, we have like three tasks, like I already told before: the state estimation, the abnormality detection, or the fault detection. So in my work, I focus on application 1 and 2. That's I use the model-based distributed state estimation and abnormality detection. And The second work is like the centralized data-driven fault detection that I use the temporal spatial recurrent rough neural network model to train the data and detect the fault. Yeah. So in the model-based dynamic state estimation, here, like the dynamic state estimation require the state-by model with non-inputs of the system. So it's difficult to get the model on component in the microgrid or active distribution network. And the input variable, we don't know exactly, but we have to measure, and these measurement come with noise, and maybe there's like some input we don't know. So the contribution in this work is just like arable unknown input gamma-based filtering in batch mode regression form. So this filtering methods can handle unknown input variable. And I also derived a state-by model of power network with dynamic model of branch current. The burst voltage I consider like an unknown input. And so I can decouple the complex network using the unknown input variable, and I implement the distributed framework to perform, and I like combine the unknown input knowledge to get the state estimation. So it can like effectively detect the abnormally or bad data in these promo methods. So for the graph learning, yeah, I will talk a little bit about that. So for contingency event, it's difficult to reduce and model. So that's why I try to use the graph neural network to learn from the data collect and detect the fault. And when we have the noise and like unincluded variable, so we cannot detect the fault effectively. The complicated and highly non-linear of the fault model is not easy to handle. So that all these difficulty lead to the methods of why we choose neural network to detect the fault. And here we use graph learning, so we can correlate the system topology with the graph topology, and that's how we have the combination of recurrent and graph convolution network to attract the fault feature. That because we consider both spatial and temporal correlation in the voltage measurement data, so that's why it's called spatial and temporal neural network. I also apply the transfer learning and fine tuning techniques in this work. So first, we will go through the distributed dynamics state estimation first. So for example, here you see in the figure, we have the power network of microgrid or active distribution network, and it can include a lot of power network, the loss, the generation units, energy storage system. So I just use the range current dynamic like the power network, and I consider the bus voltage dynamic like a non-input. So we just have for the power network model, we just have a bunch of like differential equation that is the relation between the voltage in node I and node J here, and the current go through from node I and node J. So the state-by model I have is just like on of that's range current equation. And I just consider like the voltage I have here like unknown, but it can be measured or non-measured. So if we have a PMU placed in node not I. For example, we have the measurement data of I and similar. So combines of like the power network model and the measurement from the voltage or the current, we have the global model of a power network. And also we can decouple into the local model. So if you have any question, just you can like add directly here and we can go through that immediately. Yeah. So you can see that if we have like two area and they share one node, so we have on the equation in the left into the power network of area 1, and on the model of area 2 is the power network in area 2, and the voltage in node J here just like the share input variable. And similar here, we have like multiple terminal share load, so we just consider them like a lot, and we have the share a non-input of VI and VK here. So from the state-based model, we can derive the input to output equation. That when we combine the two equation and we have just one equation of input to output equation. And when we combine with measurement equation, we have the equation of the entire system in the session number 2 here. And you can see that we can easily use the weighted least square solution for the dipole formulation, and we can easily derive the state and the input together as one. So that's why we combine the two here. The two like unknown input and also state variable in just one estimation. And we can have the estimated covariance of the stats and the input together, and we will update the reductive and covariance of the stats, and we update we have the updated estimate in equation in section 6 here. So in the equation, you can see that first we have the estimated of the unknown input in the reverse time, and then we can derive the state estimate in the time k. And we just like that, we just can like going on similar, and we always have the one time delay for the unknown input here, and we have the exact estimate for at the time k for the state variable. So for the distributed implementation, so if we implement like the state estimation into two area nearby, so first we do the local input estimation, and then we do the bad data detection here. We have the communication channel. Because like we assume that like most of the problem go through the communication channel, so that's why we put the bad data detection before we combine the input variable, and then we go through the state estimations again to get the estimate. So the step is just similar to 1, 2, and 3, 4 step here. We will have the input combination, and it also we also shows the weighted least square solution for this set of equation, and we have the covariance matrix based on this set of equation as well. And for the data detection, we check the Mahalanobis distance for the bad data detection. So to be detailed in the bad data detection here, we have to calculate the residual vector of local input estimation, and we calculate the covariance matrix. And after that, we can calculate the residual vector of input assimilation here, and we calculate the quoted RMS distance, that's the Mahalanobis distance. So we will see the difference between the input, the share input together. So from that we can tell that what is the difference between the input in area 1 and area 2. So for the loss estimation, so when we have, for example, the single loss representation here, for example, if we have the node with many lots, but we can just combine every of them into just one lot, and we calculate the power and the voltage consumption, so we can easily calculate the voltage in the lot here. And for the for the multiple terminal lot representation, we just combine them into like 2 terminal lot, and we have the voltage from node I and the voltage from node J, and the lot lie in between them. So we can run the static estimation for lot regions with data from step 1 and the data from remote terminal units, or the AMI pay measurement based on these methods. So in the methods, I use the Potsdam matrix configuration to show some calculation and simulation here. I have the Potsdam matrix 13 bus network here, and I have the hierarchy control of on 5 distributed generation units, that is the inverter by generator in node 1, node 13, node 10, node 9, and node 8. And this Potsdam matrix is simulated in RT, and we get the measurement data from the voltage sensor and the current sensor that I have in the figure here. And the measurement is added with wide Gaussian noise, and also the state and transition noises are also wide Gaussian of this number. So for the false data ingestion attack here, when we have the measurement model in this equation, if we apply the like normal static estimation using weighted least square solution here, we will see that in like some equation in the top. So you can see that when we calculate the residual, if we inject a false data ingestion attack in here, and when we have the residual RA equal to R, and that mean that our residual before and after the false data ingestion attack is the same. So we cannot see any difference if we just consider the residual for like false data ingestion attack here. And in this paper, we apply the same. We calculate an ingestion vector A here that we can carefully calculate with the S equation here, and multiply with the C number here. And in the like traditional weighted least square solution, we cannot see the difference between 2 residual. So this is the results from the local estimation, and we compare 3 methods: the weighted least square methods, the proposed state and input estimation, and the structured state estimation methods. So we can see that compare with the true data, the weighted least squares and our proposed methods is like tracking the true value is really near. And for the tracking state estimation methods, because they assume that the reverse state equal to the state value in the time in that case equal to the state value in that case minus one, and like they have a small change based on the noise. So that's why they cannot like track the state like when we have an immediate change. So here at the time second 1.5 and 1.6, here I have a really big load change. So that's why the voltage value jump up and down in the time. And here we compare the local estimate of the voltage in node 3 in D and Q coordination. And in the below figure, we have the mean square error when we compare these three methods. So the weighted least square solution and the proposed state estimation methods, they show nearly the same mean square error. But for the tracking state estimation, every time we have a load change, the mean square error jump really high. And similarly, when we calculate the mile bit distance here, we also see nearly the same value for the weighted least square solution and the proposed methods compared with the tracking state estimation. And this is the results for the input assimilation of the distributed implementation. And we see that it can track really well. Yeah. So we can conclude that the proposed methods can use similar results to the weighted least square solution, and it have like better performance compared to the tracking state estimation methods. But here the problem with the weighted least square solution, when we have the false data injection attack. Yeah, when we have that attack occur, the weighted least square solution use just a very small not use very small, but when we have the attack of occur here, so the state estimates will jump off, because we compare with the true value, we add some value to the voltage at the node. So that's why in the figure here we can see that compared with the true value, the state and input estimation, they estimate higher, and the weighted least square solution they estimate lower, and the tracking state estimation they estimate a little bit higher than weighted least square solution for the voltage in node 3 here. But when we just consider the residual, that the weighted least square solution cannot detect anything different, because like for the residual they just we carefully fabricate the attack that the weighted least square cannot see anything in the residual. But for the tracking state estimation and our proposed methods, they use a very large number in the bit distance of the residual vector. So we can see that our proposed methods can combine the accurate of the weighted least square solution, and also the ability to detect the false data injection attack similar to the tracking state estimation. Yeah. So to summarize our dynamic estimation scheme, can work with unknown input variable in distributed and active distribution system, and we use PEMD data, and we also have the distributed implementation and the integration with static estimation using the data from remote terminal units or advanced metering infrastructure to estimate the load. And we have the new form of linear gamma-based filtering methods with unknown input. Here, like I just list out some further improvement that we can consider in these methods. That because we just consider the wide Gaussian noise with like other non-Gaussian or color noise, we need to improve the noise distribution calculation. And we may apply these methods to some other non-linear filtering method like extended or unscanted gamma filter, particle filter. And we can consider the dynamic model of distributed generation unit that can include uncertainties from renewable resources like wind or solar in these methods. Yeah, so that's the end for the part of state estimation using model by, and I come to the rough learning for fault detection. So compare with the conventional neural network architecture like feed-forward neural network, convolutional neural network, and recurrent neural network that can extract the feature and learn pattern for data from a lift by and the deep learning graph can learn the feature from the rough structure data. So here we when we compare with 1D data, 2D data, or 3D data with the rough topologies by, we can see a difference that that from the topology. And when we see the rough topology data, you can see that it's similar to the power network topology. So if we apply the rough topology learning into the power system, we have the advantages of that. It's similar to the power network topology, and we can directly learn from the power network topology based on the rough topology. So in the data collection here, I simulate the power system in OrbORT. I use the Potsdam microgrid system and also the IEEE 123 not feeder, and I simulate in OrbORT. I measure the burst voltage and runs current with 1000 Hertz sampling rate with various scenarios like the fault and randomly load change. And here I just use the burst voltage. I have the Python script to like continually create the false event and collect the data, and also reprocess the data into the rough-based data sets. I use like PyTorch library to process all the data, also train the neural network. And yeah, so the data sets collect from the Potsdam microgrid and also IEEE 120 not feeder here. So for the fault type, we have like 11 fault type. For the fault resistance, we have 3 different fault resistance that 0.1, 1, and 10 ohm. And for the fault location here, because the Potsdam microgrid just have 13 nodes, so we have the fault in on 13 bursts, and we have the loss scenario randomly of 150 different cases. So in total, we have the phone cases of 64,350 that we have the lot change of 10,000. And we divide into the transits of around 57,000 fold, and the Texas of 8,580 fold, and other jet load chains. Similar to the IEEE 123 not feeder, we also have like 11 fold tie, 3 tie of fault resistance, and for the fault location, we simulate the fault like 25 knot here, and we also boost the voltage measurement in some knots here in the ring 1. And we just consider the 3-phase lines of this IEEE 123 not feeder. We don't consider like every knot or every line. That we reduce the 123 not feeder into like 3-phase line, but in the simulation we have exactly everything here. But when we model that and we collect the data, we just consider 3-phase line. We don't take any data or any measurement from the single phase, but we do have the fault location in single phase in single phase line. But when we apply oh, sorry. Yeah, in this work, I didn't have the fault in single phase line. I intended to have that in some future work, but in this one, I didn't have that. So for the robust recurrent graph convolutional network structure, we have the graph topology. So basically, we have the data sets. Y here is the data sets that we have the graph topology in G here, and we have the data of the voltage measurement from node 1 to to all of the node in the power system. And for the node that we have the voltage measurement, we have the voltage value here, but in the node that we didn't have voltage measurement, I just put the matrix of 0 here for non-measurement buses. And for the structure, so so when we have like on the data, we will go through the recurrent neural network cell and we learn the feature. And in the graph convolution neural network laser, we have the A matrix here. That is the adjacent matrix of the graph topology here. And we learn the feature H1 to Hn here, and we do the global pooling, and then we have the DEN laser for fault detection, and another DEN layer for fault ties and phase, and another layers for fault location. But in my model, I have like 3 different graph convolution neural network model for 3 different tasks. I didn't have like similar to what I throw in the figure here, like one neural network structure for all 3 tasks, but I do have like 3 different one, what nearly the same layer for RNN cells and GCN cell. That's why I will explain more in the next slide. Yeah. So when we do the comparison of neural network structure with the ANN, the long short-term memory structure, the CNN, the graph convolution network, and our recurrent graph convolution network layer. So we have the input input here, because like this is the example for Potsdam microgrids. So we have 13 nodes, and each of the nodes we have like the voltage in 3-phase ABC, and we have like 20 sample. And in the ANN, we combine all of them into just one array of 7 and 80 data here. And for the long short-term memory, we have like 39 to 20. And the dense layer, and everything just dense layer. For the long short-term memory, we have long short LSTM layer, and on dense layer. And for the CNN, we have CNN, Punlin, CNN, and Punlin, and then layer. For GCN, we have GCN layer, and on dense layer. And and for the recurrent graph convolution neural network, here we have first we have the long short-term memory layer, we have the GCN layer, and then we have 1, 2, 3, 4 different then layer for different tasks. So for the transfer learning and fine tuning here, so first we train the recurrent neural network model with phone event detection that to around 98% of accuracy here for event. And after that, the train RGCN layer, and we just train the dense layer for all the tasks. For example, here we have the phone, the neural network model for fault event. And after we train to around 98%, we copy that into another model, and we unfreeze again, and we train the new dense layer again for the fault time and phase, and also similar for the fault location. So for the training time, this is the slide for hyperparameter tuning. So when we consider the part size of the training, I try with the part size of 50, 150, 250, and 400. We can see that with the part size of around 250, we have like like fastest training time. And for the learning rate, we train with the learning rate first at 0.01 and then reduce to 0.01 after 120 epochs. So we see that it just like they have like similar results when we have like when we training with ANN and GCNN. And the results is quite good for both Potsdam power system and IEEE 123 not fit the when we compare like defined neural network structure from ANN to LSTM to CNN to GCNN to RGCN here. So we see that when because this is the time series data, so that was the long short-term memories and the GCN and our final robot methods perform a little bit better than ANN and CNN, but they all can achieve around 99.4% for full event, and also above 99% for fault phase detection. For fault time detection, that they have the accuracy a little bit lower, and especially for fault location, the accuracy is just around 92%, and our proposed RGCN it perform better than other neural network structure because we combine both recurrent and rough neural network structure. And this is the ROC curve for the default event classification. And we can see that our proposed methods is like have a better curve compared to other methods. And this is the detailed confusion matrix in the pro methods. It's quite good. We do have some like misclassification in here, but overall we can achieve quite good results with around 99-98% accuracy. And when we consider the impact of voltage measurement and also the impact of measurement noise, we can see that our proposed methods can perform like quite good results. And yeah, even when we have less voltage measurement, we can still achieve the high accuracy. And when we increase the noise in the measurement, the accuracy will also reduce a little bit. So in the summary, we just like robots, a recurrent and graph convolution network that can elaborate both spatial correlation and also yeah, temporal correlation in the data. So for the future improvement, we can consider add the current measurement, also the P and Q measurement into the scheme, and extend and explore more advanced graph learning structure. We may apply some attention mechanism into the model to improve that, but this is quite basic. So this is just like the future direction that I wrote, that we can apply, like combine the neural network and also the model base to have to improve the results for both three tasks: the state estimation, the abnormality detection, and the fault detection together. And the final slide just show a little bit about the work and projects in NREL. So like I already talked, yeah, in NREL I work closely with Dr. Rolf Hofsabian, Dr. Yas, and Dr. Sanjeev, that we own many RTDS cluster, OpenRT, real-time simulator, and the cluster of many S controller from Raspberry Pi. So we can replicate many real work system and also do a lot of real-time simulation in like large scale. Now we also have a lot of controller from from many vendor, so we can like perform many kinds of controller hardware love, and we also have the 15 kVA of linear amplifier, so we can also perform the power hardware love for many applications. Currently, myself, I'm in charge of the project for M4DC controller. That's the controller for medium voltage DC micro system. Yeah, and that is for my presentation. So welcome any comments and questions.
Thank you so much, Dr. Bang, for your talk. So while we open for Q&A, I think let me grab some questions here. Okay, let's see. For the IEEE Access paper on graph neural networks for fault diagnostics, can you explain more on why only bus voltage measurement was used as an input feature? How did you determine which bus voltage measurements to drop to 0 while keeping voltage measurements on other buses?
Okay. Yeah. So so actually this paper is just like how to say, yeah, when we play the voltage measurement or the PMU, micro PMU into the system, we can do some optimization in PMU placement. But here in this paper, I didn't do that. I just play the measurement in the bus that I consider in the critical bus. Like if we have the bus that connection in like 3 different voltage lines here and or 4, yeah, so they may contain a lot of information for all the connection. So that's why I just play the voltage measurement, and I intended to add the current measurement and the power measurement into the model, but in this work I didn't have time to like complete all of that, so I just stopped there. Just use the voltage measurement only. Yeah. And when we collect the data in the bus that we have the voltage measurement, so we have the value, and for the bus that we didn't have any measurement, so I just drop that to 0 in my calculation. So there's some suggestion when we do that, like when we can drop the voltage into 0, or in just we can use the matrix of 1, so it like not affect our learning process when we train the neural network model. But I found that if I put 1, like the training is really long, so that's why I just choose 0 for easy.
Good. We have another question. Do you consider the system as fully observable, including the micro PMU, RTU, and AMI in the static state estimation step? Follow-up question, do you have any provision for detecting topology changes?
Yeah, so first, in the fault detection using neural network, I didn't consider the observability here. I didn't consider any observability here, so I just play the measurement unit that I think that may enough, and I just perform the data learning for that, and yeah, and process the data. For the state estimation, we do have to consider the observability. So let's come back to the model by state estimation. So my final equation is this equation, the C0, D0D, CA, and CB here. So this matrix have to be like observable, like otherwise we cannot use weighted least square to show the equation. So if the equation is solvable, that means our system is observable. Otherwise we have the unobservable problem for the state estimation using model by. For the data driven, we didn't consider the observability. We just play the voltage measurement, learn from the data, and go from that.
Is there any provision for detecting topological changes?
Yeah, no, here like I have no any consideration for topology change. Yeah.
Good. Can we go back to your current projects at NREL? I have interesting questions on, what, some similarity, how we can find ways to collaborate. We have
Yeah.
we have 2 DOE funded projects, and where we are putting together an edge test bed for different DERs and trying to model different cyber attacks on Modbus protocol and developing some AI to detect certain X and Y attacks with COMET and ANL. We have this project going on. But I'm just curious, the other test bed that you talked about, Opal RT and RTDS. Can you go to the next slide? I want just to show you, understand. Oh, you have 600 Raspberry Pi in your edge thing?
Yeah.
Okay.
We currently we have 600, and we are expanding to 5,000. Then we use big scope rack, and we have a lot of them, but not so in the picture here.
Can we stay on this slide? Or this slide? Like, yeah, I think so.
Yeah.
You have RTDS, you have all these
Yeah.
smart meters. So how can UND can work with you on connecting our test bed, to, we have this test bed containing with NVIDIA's AGX and nanos and embedded devices. But I'm trying to connect to different RTDS and OPAL systems across different universities, and I was wondering, do you have any interest in working with us on maybe, connecting to some of your system to figure out, look at maybe a secure way to transport packets on certain communication protocols that you have for this microgrid projects,
Yeah. Yeah, I think the best way that I will connect you with me, Sanjeev, Yas, and Rolf, and you can like take a visit to NREL to see like the setup and everything, and we can discuss more the collaboration from them. I think that's the best way. Yeah. Yeah, I
Okay,
can add
so
Rolf.
you have a collection to the smart meters that is this test bed that you have on the on the bottom. You have this at NREL, what I see, like
Yeah,
smart
yeah.
meters
We
communicating
have
like.
many cluster of RTDS and Oppo RT and Typhoon, the vendor controller, and also many rack of Raspberry Pi, like 5,000 of them, and we are spending a lot. So we own like nearly on the ARIS access. You know about ARIS?
Yeah.
If you know ARIS, so yeah, we own like nearly on the access of like real-time simulator in ARIS. Yeah.
Cool. What about the next slide? Can you show me the next slide? I'm just curious. What
Yeah,
about
and we also have the new amplifier, power amplifier here. They just come from last year. Yeah.
So
Yeah.
these are like behind the meter yours FTM. What is FTM? What are these racks that I see here? What are these?
Oh, so this is like I copied the slide from the like behind the meter and front of the meter. So so they use that for that project. So they use the power amplifier to demonstrate the load prediction or the prediction and analytics in behind the meter or front of the meter. Yeah. But yeah, that's just like leverage of the power amplifier here. The amplifier we have like 12 of them, so we can config into many like AC or DC, and we also have the thing here just like the inverter, bidirectional inverter. They have the DC-DC and inverter rectifier together. So so from the access we can set up many power how and the love and loop with the controller and stuff like that.
Is it a
And
particular vendor inverter? This one?
yeah, this is from Optech. Yeah, this is the vendor inverter, but they not for commercialized in industrial.
Sure.
They are like universal inverter and converter for the left.
Octec? Okay, that's interesting. Okay.
Yeah.
Cool. I think I will do a follow-up meeting with you and maybe we can find ways to synergize to do this. Okay.
Yeah.
Anything else? Okay. Any other questions do we see on this? Okay. If not, I think thank you for so much, Bang, for your time today. You will receive a nice plaque from UND, and hopefully we can touch base with you as we work on other proposals and other opportunities for us.
Yeah. So welcome to do that.
Thank you so much.
Thank you very much. Yeah.